The next problem says, what is the relationship between electric and magnetic fields in an electromagnetic wave? Okay, the first option says they are independent of each other, and this is not correct. They are perpendicular to each other and the direction of wave propagation, and this is the correct option, and I will explain why. Let's say I have this plane that has electric field, and then the electric field is vibrating here, and then I have this plane for magnetic field, and magnetic field is vibrating here. Then I will have the wave will I will have the direction of wave propagation here. Okay, the wave will propagate in between them, and then the electric field will make angle 90 degrees with this direction. The magnetic field will also make angle 90 degrees with this one. That is the meaning of perpendicular, making angle 90 degrees. Okay, so electric field is making angle 90 degrees with the wave direction of wave propagation. Magnetic field will also do the same, and between electric and magnetic field too, you have 90 degrees. So they are mutually perpendicular with each other. This and these are perpendicular, this and these are perpendicular, this and these are perpendicular. This is why the second option is correct. They are perpendicular to each other, meaning electric and magnetic field, and the direction of wave propagation. So next problem says, what is the direction of the magnetic field lines around a current carrying wire? We explained this one is circular around the wire. It should be circular around the wire, circular, radially outward, no. Perpendicular to the wire, no. Tangential to the wire, no. We just explained earlier that if I have a current, okay, this is a conducting wire and current is flowing through this wire in the upward direction, then circular around the wire you have magnetic field. Okay, you have magnetic field here. Okay, and you can use the right hand rule to determine the direction of the magnetic field. The thumb should point in the direction of the current, and then you curl your finger. Let's say this is my the current is flowing through here. This is my wire, and then my thumb should be in this direction. Then I curl my finger like this. You see? Okay, this is the direction of the current, and then here this will give me the direction of the magnetic field. So it is circular. Okay, it is circular. This is the correct option. Next problem, moving on to the next problem, it says, I like this so very much. It says, what is the direction of the magnetic force on a positive charge? Look at it, on a positive charge moving in a magnetic field. Now, what will be the direction? We have to do a little study here. Okay, let's say I have a plane here. Okay, and here I have magnetic field, uniform magnetic field B. If I bring a charged object, and then this charged object, let's say, is a positively charged object, and the positively charged object is moving in this direction with a velocity v, which means in the same direction as my field vector, all of them in the same direction, there will be no magnetic force on my charge. Okay, there will be no magnetic force on my charge. If again I bring it the charge into the field, but the charge is at rest, is stationary, is not moving, again there is no magnetic force on my charge. But now look at this one. Let's say I have a magnetic field here, and I bring the charge when I bring the charge here, the charge is moving in this direction, so that the velocity is here. The angle, it makes angle theta with the magnetic field. Then it will experience a force, and this force will be in such a way that this is the direction of the force. The force is perpendicular to the field, and it is also perpendicular to the direction of the charge motion. The charge is moving along here, so the force will be upward, okay, and makes angle 90 degrees with the direction of motion. So that is if the charge is positive. If the charge is negative, the force, the magnitude of the force is the same, but it will be in the opposite direction, downward here, minus F. Okay, so this means that the force is equal to the magnitude of the charge multiplied by the cross product of the velocity vector and the field vector. This will give me the force for a positive for a positive force. Now my F will now be Q B cross V. You see, if this is for a positive charge and this is for a negative charge, I have to reverse this, and if I reverse this one, my answer will just be same as the other one, V cross B, okay, but I have to put a negative sign here, okay, and this is why we have minus here, okay. At least we know that the force makes angle 90 degrees with the field, and then it makes angle 90 degrees with the direction of the charge motion. Okay, having said that, let's see what is going on here. Let's read the problem again and see how we can solve it. It said, what is the direction of the magnetic force, the direction of F on a positive charge? Okay, you have a positive charge moving in a magnetic field B. Okay, the first option said in the direction of the particle's motion. No, perpendicular. I like this word, perpendicular to the direction of the particle's motion and the field, and that's exactly what we saw. If the field is in this direction and the charge is moving in this direction, okay, then the velocity, the force will be here, F, okay, so that it makes angle 90 degrees with this and also 90 degrees with this. The angle between B and V is theta. Okay, so this is the correct option. Moving on. Great. This problem says find the magnetic force. They want you to use the formula to calculate magnetic force. Find the magnetic force experienced by an electron. You have an electron. An electron carries a negative charge projected into a magnetic field of flux density 10 Tesla with a velocity of 5 times 10 raised to the power of 7 meters per second, parallel to the magnetic field. If it is parallel to the magnetic field, it means it is in the same direction. The electron is moving in the same direction with the magnetic field, you see? And we say that any charged particle moving in the same direction, okay, as the magnetic field, then the force, the magnetic force on that charge is zero. So without any calculation, you know that this has to be zero. Okay, but at least for the for further clarification, let's do the calculation. F is equal to Q V cross B, okay, and then this is Q magnitude of V, magnitude of B, sine of angle between V and B, sine theta, meaning this theta. Look at it here. You have the V, you have the B, the angle between them is theta. So magnitude of V, magnitude of B, multiplied by the sine of the angle between them. Okay, now if they are parallel to each other, your theta is 0 degrees. So this is equal to QVB sine sine 0 degrees. If you check your calculator, sine 0 degrees is 0. Okay, so this means you have QVB times 0, and this reduces to 0 Newton. Okay, this is 0 Newton. Whatever the value of Q, V, and B that you have, when you put all of that and you multiply by 0, you get 0. So the correct option is the first one that says 0 Newton. This one is not important, it's only a distraction, and so are these two. They are only distractions. Okay, your answer must be 0. Okay, thank God we are moving forward, we are making progress here. Okay. Okay, I told you earlier that you can generate electricity using a magnetic field, okay, using a magnet and a coil of wire without the use of a battery, okay, and we call this process electromagnetic induction. In electromagnetic induction, we have two basic laws. The first one is the Faraday's law of electromagnetic induction, established by Michael Faraday, the English physicist. The other one is the Lenz's law, which we will see later. Okay, we are going to solve this. It's one of the problems we will solve here. Okay, the first one is Faraday's law and the second one is Lenz's law. What is Faraday's law all about? Okay, Faraday's law, to understand Faraday's law, before we go to the English of it, okay, before we go to the English of it, let's say we have a coil of wire here. Okay, this is a coil of wire, and then let's say again we have a magnet here. Okay, this is the north pole of the magnet and this is the south pole of the magnet. We know that we have magnetic field lines here, and the field lines are linking with the coil here. Okay, the field lines are linking with the coil. Okay, they are linking with the coil. Okay, this is a magnet and this is a coil. Michael Faraday says if there is a relative motion between these two, then current will be induced here. There will be current here induced, and there will be a potential difference, induced EMF between the two ends of the wire, which create induced current flowing through the coil, generating electricity. But the condition is that there must be a relative motion between the two. How do I have a relative motion here? If the two of them are moving together with the same velocity, no relative motion. Okay, let's say both the magnet and the coil are moving at the same time and with the same velocity, they are not moving relative to each other, and there will be no induced EMF and current. Secondly, if they are both stationary, this one is not moving, this one is not moving, again there will be no induced EMF, no induced current. But if I keep one stationary and the other one is moving, I can decide to keep the magnet stationary and then I move the coil towards the magnet or away from the magnet, then there is relative motion now, and current EMF can be induced now. Or I keep my coil stationary and I move the magnet towards the coil or away from the coil, again there will be induced EMF, okay, and induced current. The thing is that if these lines linking with the coil change, because if I bring it forward, the number of lines will increase, linking with the coil will increase, and there will be more EMF. If I bring it back again, if I push it away from the coil, the number of lines will reduce, and I will still have, of course, EMF. So this the rate of this linkage is what we call d phi dt. Okay, d phi dt. Now what Michael Faraday is saying is that look at it here, the first option, the rate of change of magnetic flux, meaning d phi dt. The phi is the number of lines linking with the coil here, number of the field lines, magnetic field lines linking with the coil. Okay, and then the phi dt is the rate of change of these lines per unit time. Okay, if this rate increases, there will be more EMF. They said the rate of change of magnetic flux through a loop of wire induces or creates an electromotive force, meaning EMF, which is the potential difference between the end of the wire that is necessary to cause current flowing through the wire. So in other words, this is what we write as the equation. The EMF created here is equal to negative N, where N is the number of turns in the coil. So if I have only one turn, one loop of the wire, N is 1 and I can remove it. So this is d phi dt. So if this is changing, I will have EMF, and this is why I have to move this close to the wire or away from the wire, because there must be linkage, there must be change in the number of lines linking with the coil before I can have my EMF. Okay, if this is why we said if they are stationary, it is 0, there will be no EMF, because if they are stationary, there is the linkage, the flux is constant, and if the flux is constant, d phi dt, because it is constant, you see, remember the derivative of a constant is 0, you see. So if it is constant, d phi dt will be 0 and my EMF will be 0. And when will it be constant? It is when the magnet and the coil are stationary, or they are both moving with the same velocity. Okay, so when that happens, my rate of change of flux will be 0, magnetic flux will be 0, and the EMF will be 0. But if it is changing, whether increasing or decreasing, I will have my EMF. So the first option here is my answer. The rate of change of magnetic flux through a loop of wire induces an electromagnetic force. So with this, it means I can create electric current and an EMF just from the magnetic field that I have here, okay, without the use of a battery. Next, the formula for Faraday's law of electromagnetic induction is, I just gave you the formula, look at it here. Only that if you have only one loop of wire, then your N is 1, and if this becomes negative, d phi dt. But we normally put N so that it will be a general formula. Okay, so here are our options, and you can see this is the correct answer. Not this one, not this one, not this one. Okay, now all this while I was silent about the negative sign in the Faraday's law. There is a question on that. It says, what does the negative sign in Faraday's law of electromagnetic induction indicate? What does it indicate? What does it mean? The first option says induced voltage and the induced current are in the same direction. If they are in the same direction, why will it be negative? No, induced voltage and current are in the opposite direction of the change in magnetic field, and this is the correct option. Okay, if the change is in the magnetic field is in this direction, then the induced EMF should be in the opposite direction, and that is why you have a negative sign in the formula. Okay, next, the equation for the force experienced by a charged particle in a magnetic field is, okay, this one comes from Lorentz force. Don't forget, if for Lorentz force, F is equal to Q electric field plus the cross product of these two. Now, that if it is only magnetic field, because here they say in a magnetic field. In a magnetic field, you don't have this electric field, so E is 0. So I have Q into V cross B. Okay, everything here vanishes. So I know that this should be Q magnitude of V magnitude of B sine of angle between them. So the force on the charged particle moving in a magnetic field is F is equal to QVB sine theta. Then I look at the options and I see that this first option is the right one, and I take it gladly. I cancel this, I cancel this. This is a special case. Remember I said it earlier. This is a special case when your theta is 90 degrees, so that sine 90 degrees is 1, and if I put 1 here I get QVB, which is this one, but this is more general, so I take this one. Now the next one says a horseshoe magnet is an example of what kind of magnet? Is this a natural magnet or artificial magnet? Neither natural nor artificial. None of these options. The correct option is artificial. Okay, a horseshoe magnet is a kind of magnet that looks U-shaped. You normally see in the lab. We call it horseshoe magnet. Okay, it's a man-made magnet. Okay, here, wow, I like this problem. Here we are going to use the equation above to solve a problem. Here we are going to use this very equation, this one, to solve a problem. It says if a charge of 2 coulomb, you have a charge of 2 coulomb, is moving with a velocity 5 meters per second. This is the velocity. Okay, perpendicular means it makes angle 90 degrees to a magnetic field, and the magnetic field has this value 0.8 Tesla. So this is your B. What is the magnitude of the force, meaning what is F experienced by the charge? So as quickly as possible, we just say F is equal to QVB sine theta, and this is equal to our Q. Our Q is 2 in coulomb, 2. Our V is 5 in meters, 5 per second. Our B is 0.8, so we have 0.8, and then multiplied by sine what? Theta, and our theta is 90 degrees because they mention perpendicular. So if you take your calculator and multiply all this together, you will have 8 Newton. Okay, you will have 8 Newton. 2 times 5 will give you 10. 10 times 0.8 will give you 8. Sine 90 degrees is 1, so 8 times 1 will be 8 Newton. Simple as that. So let's check our options, which one has this 8 Newton, and we will take it. Anyone with this 8 Newton, we will take it. Whoa, great. So this one has the 8 Newton, so I take it. Take it. I don't take this, I don't take this, I don't take this. Now we are making progress, and I love it. Okay, you are going to see something different here. Here it says that if a 0.5 meter wire carrying a current of 4 ampere is placed perpendicular to a magnetic field of 0.6 Tesla, what is the force experienced by the wire? Okay, this one is not just about even though of course it's about charged particle, but it's a bit different. In a conducting wire, let me bring something like this. Let's say I have uniform magnetic field. This is my magnetic field. Okay, forgive me. Let's assume this is my uniform magnetic field of magnitude B. The magnitude of this field is 0.6 Tesla. Now I bring a wire here. Can you see? This wire carries current, and the wire, I bend it like this. In the magnetic field, let's say from the length of the wire from here to here. Okay, I want you to understand that only the portion of the wire that is in the field will experience the force. The portion that is not in the field will not experience the force. So the length where they are talking about is the length from here to here. Okay, this the length of the wire, L, and the length of the wire, okay, the length of the wire is what? 0.5 meter. Okay, now this and the wire, don't forget, carries a current in this direction. Okay, and the current carried by the wire is 4 ampere. The magnitude of the current is 4 ampere. Now clearly your wire makes angle theta with the magnetic field. This is the magnetic field B, this is your wire, the angle between them is theta. Now this wire will experience a force. How do I get the magnitude of the force? I will use a formula that says F is equal to BIL sine theta. Say you are going to see something new. B, the magnetic field here, I, the current it carries, the wire carries, and then L is the length of the wire. And remember, this length I said is the portion of the wire in the magnetic field. So this is equal to my B is 0.6 times my I is 4 times my L is 0.5 times sine theta. This is sine what is my theta? Look at, okay, you have to check the English there. If they say perpendicular, your theta is 90 degrees. If they say parallel, it is 0 degrees. Okay, now this is sine 90 degrees. So if you calculate this correctly, you have 1.2 Newton. Okay, your answer should be 1.2 Newton. And then check the options here. This is 1.2, the first one. Oh my god, I don't take this, no. Okay, another interesting formula, interesting phenomenon. Okay, it says, which equation represents Gauss's law for magnetism? Is it this one or these ones that we see here, or these ones that we see here? Look at them. Which one? Okay, I am going to tell you now that the correct option is the first one. This is the Gauss's law for magnetism. Okay, Friedrich Gauss had many laws. He had one for electricity, and there is another one for magnetism. The one for electricity was the one that we said flux, the electric flux is equal to enclosed charge divided by epsilon naught. Another way of writing this is to say integral E, okay, is to write it this way, dot dA is equal to enclosed charge divided by epsilon naught. Okay, what this means is that since it is not zero, it means I can isolate a charge. I can isolate a positive charge. I can, isolate a negative charge. Okay, I have an inward flux here, and here I have outward flux. Okay, but for magnetic field, the equivalent of positive and negative for a magnetic field is north and south. Okay, north and south. So divergence of B for magnetic field is equal to 0, and this means that I cannot isolate one pole away from the other. I cannot have a monopole. I cannot have a single north pole or a single south pole. If I have let's say this is a magnet, this is the north pole, this is the south pole. I know that the lines of force, magnetic lines of force, are like this. Okay, so uh, something like this. Okay, great. So if I say, del B, I am trying to investigate if at all I have enclosed magnetic charge here, and it's impossible. I don't have magnetic charge anywhere here, so this has to be 0, and that is the Gauss's law for magnetism, that it indicates absence of a monopole. But of course, for charges is non-zero for electricity, but it is 0 for electricity. So this means another way, if you compare it with this, the one for electricity, you can say integral here B instead of E, because this is for electricity and this is for magnetism, dot dA, and this is equal to 0. This should be 0 and the other one is non-zero. So this is our option here. This cannot be my option, this cannot be my option, this cannot be my option. Okay, now we are taking the next problem. Okay, let's say we have a solenoid. An iron core solenoid with 2000 loops. Okay, this is the number of loops, n, and then is 60 centimeter long. The length of the solenoid is 60 centimeter. If you divide this by 100, you will get 0.6 meter. Okay, and to the SI unit, and a diameter, I may not need this one. If a current of 5 ampere is sent through it, what will be the flux density within it? Okay, the flux density within it. Okay, in other words, what will be the magnetic flux in Tesla, because you what you have here in Tesla. So for a solenoid, the magnetic field within the solenoid is given by mu naught, or you are not given this. This should be mu naught. This is a constant and you should always be given, times 10 raised to the power of -7 Tesla meter per ampere. Okay, so Ni, okay, where mu naught is the magnetic constant here, this N is the number of turns or number of loops per unit length, and I is the current through the loop. So this N, I say, is the number of loops per unit length of the solenoid. So if you put it there, it becomes mu naught into N over L, because this N is capital N over capital L, and then multiplied by the current again. So I can combine this times this times this, so I have mu naught Ni over L. Okay, now I can substitute what I have. This is 4 pi times 10 raised to the power of -7, that is for this, and then my N, the number of loops from the problem, 2000, so I have 2000 here, and then I, the current flowing through it, I was told 5 amperes, so this is 5.0 in ampere divided by the length, and the length is 0.6. You see 0.6 in meters. This is 0.6 meters. Now mashallah. Now if you calculate this correctly, you're going to have 0.021 approximately in Tesla. Okay, let me see how we can do that. You just open bracket. Okay, you open bracket and say 4 shift pi, okay, times 10 raised to the power of -7 close bracket, okay, then times open bracket 2000 close bracket, then open bracket again, 5.0 close bracket, then press the division line, and then you now have 0.6 divided by 0.6, and look at what you have here, 0.0209, approximately 0.021, correct to two significant figures. And my correct option is the second one. Okay, Biot-Savart law is related to the Ampere's law that we learned earlier about. You have a current, you have a wire, okay, carrying current, and then the magnetic field is rounded, and you use the right hand rule to determine the direction of the magnetic field and at any point the magnetic field B is given by mu naught I divided by 2 pi r. We derived the formula earlier. Okay, this is also can also be deduced from what we call the Biot-Savart law. Biot was a scientist, Savart was also a scientist, so we use their names to honor them. According to Biot-Savart law, the formula for the magnetic field B produced by a long straight wire carrying current I at a distance r from the wire, the formula is B is equal to mu naught I divided by 2 pi r. Okay, and we used the formula before. Is that it? So you check these options. They are given 4 options and only one is right, and it's the first one. Oh my god, I love this formula. Okay, next, which of the following laws is the consequence of the law of conservation of energy? Wow, we are back to electromagnetic induction. I told you that we have 2 fundamental laws of electromagnetic induction. The first was the Faraday's law, and the second is the Lenz's law. So the Lenz's law is one of them, and it is a consequence of the law of conservation of energy. How is that possible? Okay, first of all, what is Lenz's law? Lenz's law says that the induced okay, let me make it clear to you now to be able to understand the importance of the 2 laws differently. Faraday's law, we use it to measure, to quantify the induced EMF, because from that law we got a formula that says the induced EMF is negative N d phi dt. So clearly we can quantify it. We will know how much of the EMF that we have. Then Lenz's law tells us the behavior. Is not quantifying the EMF, but it is telling us how this EMF behaves. Okay, and in doing that, we are made to understand that it is actually a conservation of energy principle. Okay, and let us go back to the magnet and the coil thing for more clarification. Let's say I have a coil here and I have my magnet with this is the end pole of the magnet. Okay, according to Lenz's law, this EMF, okay, this EMF acts in such a way to oppose the motion creating it in a direction so that it opposes the motion or the change that is creating it. And I'm going to demonstrate that here. I have the knot here, the knot pole here. If I push this magnet, this is a knot pole. If I push this magnet here, then my EMF that is induced here will tend to oppose the motion of this magnet that is creating the EMF. Okay, but how is it going to do that? It means that this one should also, this end of the wire should behave like a knot pole, so that it can now push it away. so that there will be repulsion. Okay, if I bring it forward here, then this one should push it in this direction, so it has to create a north pole here. This will behave like a north pole, and then the current will flow like this. You see, this means that the current will flow like this, okay, like this, okay, like this down, okay, so that it can oppose it. But where is the conservation here? The conservation here, okay, I will explain that. If I try to push this one towards the wire, and then the wire create a north pole here, a temporary north pole here that is pushing it, I can feel the repulsion. So I have to put in extra force to overcome the repulsive force. Now if I put an extra force, I now move the magnet towards it. I have the force, and then I move the magnet towards it through a distance s. Then the mechanical work I have done is force times distance, force times distance. Now this mechanical work is converted into electrical energy. This is the work I have done in overcoming the repulsive force. Okay, this force from my hand, and then this distance moved by the magnet is the mechanical work, is the measure of the mechanical work I have done. This mechanical work is converted into electrical energy in the materials of the wire, electrical energy, okay, so that I can have induced EMF, so that I can have current flowing through the wire. Again, if I try to, let's say I have north pole here, south pole here, and then I have my loop I have my wire loop here. Now if I try to push it away from the wire, now this wire will behave in such a way that it will oppose it. It means it will try to push it in this direction. I'm pushing it in this direction, it will try to push it in the opposite direction. So here will create a temporary south pole, so that it can attract my north pole. You see that? When that happens, as I am trying to push it away, I can feel the attraction. So I will add extra force to push this magnet away. So that force multiplied by the extra force I added, multiplied by the distance moved by the magnet, will be the measurement of the mechanical work I have done. Now this mechanical work done will not be wasted, will not go in vain. It is this work that is converted into electrical energy in the materials of the wire, and the current flows like this. You see, okay, so current flows like this, like this, like this, down in opposite direction. So when I am pulling it in this direction, the current is in this direction. You see, opposite. When I am pulling forward, you see, forward here, the current is here. You see, so it is moving in such a way that it opposes the motion or the change producing it. And this observation was made by Lenz, and we named the law after him. Okay, it's not Ohm's law, it's not Archimedes' law, and it's not Ampere's law. Okay, finally, when the charged particles move, let me remove this there. It's not it's not necessary. When charged particles move in a combined magnetic and electric field, then the force acting on those charges is known as, okay, you know that force already, Lorentz force. Let me give you the answer before we check. Lorentz force, we already saw that earlier, is Lorentz force. Okay, here are our options. The first one say centripetal force, no. Centrifugal force, no. Lorentz force, yes. Orbital force, no. So with this one, I hope you know a lot about magnetism in physics. Thank you for watching. Assalamu alaikum wa rahmatullah.